Uh, Dear students, today we are going to discuss some of the topics on statistical model in simulations. So, if you remember, we have given some of the examples on in module number one, which were talking about system, attributes, entity, and so and so forth. So, in that particular scenarios, you take any system. So in system you will have so many number of entities, and every entity is going to perform certain actions. So in few situations where we can predict the actions which are performed by these particular entities completely. So that is what we are seeing first point. In modeling real-time world phenomena, so there are few situations where the actions of these entities within a system can be predicted, which are under consideration. So all these actions, whatever we are going to predict, these are all the probabilistic rather than deterministic. Now, consider one example where there is a particular, breakdown of a particular machine. So, what are the different causes for this? The first, in order to get this particular machine repaired, we have certain possible options. So, if you look at the time it takes a repair person to fix a broken machine is a functional of complexity for this particular breakdown. Now here, whether this particular repair person has brought the proper replacement parts and tools to the particular site is one thing. Second point is whether the another repair person asks for assistance during the course of a repair. So third point is whether the machine operator receives a lesson in preventive maintenance and so forth. So basically, if you want to get the things done or gets repaired, first you will call for a repair person. So first, we'll check like after he comes over to the particular site whether he has brought all the toolkits or not. That you are going to check it out. So after that, whether he is able to do it or not, that we will going to check it later. If he is not able to do it, then is it required to get another repair person's assistance? Second point. Third point is like whether he has brought the proper repair toolkits or not. That also you are going to check it. So like this, there are so many number of questions will be posed to us. Okay. So for a particular model builder, okay, all these variations appear to occur by chance and cannot be predicted. So this is very important where in such cases some statistical model might well come into picture to take the different times and to make this particular repair. So always it is not like probabilistic and cannot be predicted. So if you order somebody or for a particular repair, so in over the phone he will ask you like what are the different what are the different things that are happened to that particular machine. So based on his experience, so he will try to identify what is the a bug. So now, usually these appropriate models can be developed by sampling the phenomenon of interest. Now, all these can be done with thorough educated guesses, maybe using the software for this particular purpose. The model builder would select a known distribution form, make an estimate parameters of this particular distribution, and get a test, and then test to see how good if it has been obtained. So that is what we were talking about, the previous model. So now through this continued efforts in the selection of an appropriate distribution form and the different kind of postulates models could be accepted or could be generated. Now these are all the different contents what we are going to study in this particular module. So discrete random variables. Then we are going to talk about continuous random variables, cumulative distributive function, then expectations, then Poisson's distribution, and so on and so forth. Now, coming to the first part. So these are all what already we have studied, but still as uh, a review of various terminologies and concepts. So we are going to talk all these kind of things. Now consider X be a random variable. Okay, and if the number of possible values of X is finite or countably infinite, then X is called as the discrete random variable. So possible values of X may be listed as X1, X2, X3, X4, so on and so forth. So in finite case, it will terminate somewhere, and in case of infinite, so it will continue indefinitely. Now consider one example wherein which the number of jobs coming for a particular shop. You take any example. So in this particular shop, the random variable of interest is X. Okay, where this X is number of jobs arriving in a week, each week. Okay, so now the possible values of X are given by the range space called as Rx. Okay, range space Rx. So what might be the Rx value? So here for this particular case, I can have 0, that is no number of jobs, 1, only one job, 2, 3, 4, 5, 6, 7, 8, 9, 10, something like this. So you have the Rx values. Now, in order to define properly, okay, let X be a discrete random variable, okay, which is finite or it can be infinite, with each possible outcomes xi in Rx. So there are some possible outcomes. Okay, whether what are the possible outcomes? Maybe 0, maybe 1, or maybe 2. A number p of xi, where p is equal to x of equal to xi. So p of xi may be like any value. Okay, so which is given in Rx. So this combination of xi and p of xi gives the probability that a random variable is equal to the value of xi. So now the numbers p of xi, comma I is equal to 1, 2, 3 must satisfy these following conditions. Now if you look at p of xi value should be always greater than or equal to 0 for all value of I. So for all I, it is not 1 I. Second case, summation of I is equal to 1 to infinity. So that depends on how many number of values are there in xi. P of xi equal to 1. Okay. Now the collection of various pairs xi and p of xi is called as probability function of x. Okay. So now the p of xi is called as the probability mass function, that is PMF of x. So now for this particular problem, we are going to find out xi, what is p of xi, and how to draw that particular graph for related to xi and p of xi. So hope it is clear. So any probability function and probability mass function. Now consider another example, uh, which is tossing a particular die. Okay, when you toss a particular die, what are the possible values of x, that is define x as the number of spots on the upper face of the die after a toss. When you toss a particular die on face, on top, what are the possible numbers that will occur? So you have different 1 to 6, so your values of x should be up to 1 to 6, so which is always greater than 0. So that is why your Rx value. So if you look at what are the total possible number options, so total may be like 6 plus 5 plus 4 Values Rx equal to 1, 2, 3, 4, 5, 6. So if you add all this, so that is 21. Okay, now assume that this particular die is loaded so that the probability that given phase lands up is proportional to the number of spots showing. Now with this particular experiment I can know that xi is equal to 1, 2, 3, 4, 5, 6. P of xi value is 1 by 21. So probability of xi is 1 by 21. This is 2 by 21. This is 3 by 21. 4 by 21. 5 by 21. 6 by 21. Combination of xi and pi. When x is equal to 1, so p of xi is equal to 1 by 21. Okay, like this, I have found the values of 1 by 21, 2 by 21, 3 by 21, 4 by 21, 5 by 21, 6 by 21. Now, if you look at the previous conditions, first condition to be a random variable should be p of xi should be always greater than or equal to 0. When you look at all these values, so it is always greater than or equal to 0 only. Then if you add summation of 1 is equal to I is equal to 1 to infinity p of xi should be equal to 1, should be equal to 1. So now if you find all these values, you are going to get is equal to 1. So now when I draw a particular diagram against xi value with the p of xi value, I am going to generate this particular graph, okay, which will define the probability mass function for a loaded die example. Now, so this is where you are going to get the discrete values, which are discrete. Now there is another one. When you draw a graph, it will not be a discrete; it should be a continuous. So now that is what we are going to talk about, a continuous random variable. So if the range space x Rx of some sample random variable is an interval or a collection of various intervals, okay, so then x is called as continuous random variable. So that is, it should be a continuous. So now how you are going to represent this continuous? That is with the form of limitations. Under the area under a particular graph can be identified with this particular limitations. For a continuous random variable x, the probability of x lies in the interval a comma b, a comma b, which is given by P A is greater than or equal to x less than or equal to b, which is given by integration of a to b f of x dx. I'll call this as equation 1. This function f of x is called as probability density function of a random variable x. Now here in the previous case xi comma p of xi, and here it is now p of a greater than or equal to x less than or equal to b, which is a to b, integration of a to b f of x dx. So now in order to write a particular PDF, this PDF will satisfy these three conditions. Condition 1, if you look at your f of x should be always greater than or equal to 0 for all the values of x in Rx. Then second one is the integration of Rx f of x dx equal to 1. Then f of x is equal to 0 if x is not in Rx. Okay. So now 1 for any specified values of x naught, I can write integration of x naught to x naught f of x dx equal to 0. So this is what one thing what you need to remember here is integration of a to b f of x dx. How you are going to represent this particular random variable. Now, if you look at when you draw a graph, x is equal to a and x is equal to b against x to f of x, you are going to get this particular diagram. So, if you look at the shaded area represents the probability that x lies between or lies in the interval of a and b. Now, after knowing the different types of variables, how these different variables can be distributed, so which is something called as cumulative distribution function. So you will be knowing what is xi, and you will be knowing what is p of xi. Then what is meant by the cumulative distribution function? So if you look at the cumulative distribution function CDF is denoted by f of x, measures the probability that a random variable x assumes a value less than or equal to x. Okay, that is f of x should be, I can write it as p x is less than or equal to x. Usually if you look at if x is a discrete value, so I can write f of x. So here x is equal to this value x for all the values I greater than or equal to x, p of xi. So basically this here cumulative distribution function in case of discrete function is it is a summation of all the values of p of xi. Okay, I will call this as equation number 3. And in case of uh, uh, this, the data is continuous. In that case, f of x is equal to, I can represent it as integration of minus infinity to x f of t into dt. So I will call these two uh, equations as cumulative distribution function. Now, there are some properties which are listed out uh, for CDF. So, some properties of this CDF are listed here. If f is a non-decreasing functions, okay, that is if a is less than b, in such case I can write f of a less than or equal to b, f of b. Second one is limit of f of x is equal to 1 if x tends to infinity, and it is f of x is equal to 0 if x tends to minus infinity. So now with this I can answer all probability question about x can be answered in terms of CDF, that is probability of a less greater than x less than or equal to b. I can write it as f of b minus f of a for all a is less than or less than b. Okay, I will call this as equation. So to compare with what are the different discrete the comparison between the discrete random variables and continuous random variables, I have written here. So any sample space, okay, what is the sample space? Any event, so which can be written as 1 0 1 2 3. For a dice you will have tossing up a particular dice, your value will be like 1 to 6. Then here you can have any there is infinite sample size, but the thing is there should be a certain limits, whether it is 0 to 1 or 2.1 to 5.3. So this is upper limit and this is sorry, the lower limit, and this is upper limit. So like this you are going to represent continuous random variable. So probability mass function is used to define discrete random variables, which you are already aware of. P of xi is equal to this one, and p of xi should be always greater than or equal to 0 for all the values of I. And here we are going to find out I is equal to, this is important, I is equal to 1 to infinity, p of xi is equal to 1. But at the same time, if it is a random variable, instead of using probability mass function, we are going to represent with probability density function, which is f of x, so which is always greater than or equal to 0 for all the values. So f of x greater than or equal to 0 for all x in Rx. So integration of Rx f of x dx. So now this is what the cumulative distribution function what we are going to write. These two are the formulas. Now one topic which talks about the probability density function along with the probability density function, which is something called as expectations. An important concept which talks about the probability theory, or which is in probability theory, which is something called as expectation of a particular random variable. If x is a random variable, then the expected value of x is denoted by e of x. Whether it is a discrete random variable or whether it is a continuous random variable, we are going to represent e of x as expectations. So you should remember all these two formulas, very important. So if x e of x is no if x is a random variable, then e of x for a random variable is just summation of all I with xi into p of xi. Okay, so value of xi will be given, value of p of xi will be given. You have to find out e of xi. Hope it is clear. So if it is a continuous random variable, then it is an integration of minus infinity to infinity x into f of x dx. So there should be there might be a problem which talks wherein which you are going to find out the values of ex. Now I'll call this as equation number 6 and I'll call this as equation number 7. Now, okay. Now, if you look at here, the expected value e of x of a particular random variable is also referred to as mean. So now we are on track. So we have to find out the mean value and the variance for the different types of random variables. So the e of x, that is mean, mu, or the first moment of x. Okay. So second point is the quantity e to the power of x, e of x to the power of n, where n is greater than or equal to 1, is also called as nth moment of x. Okay, nth moment of this. E of x to the power of n equal to e of sigma of xi to the power of n p of xi if x is discrete. So as I told in the previous class, that is in the previous slide, and here e of xn equal to integration of minus infinity to infinity x to the power of n p of xi. So basically you are please remember this is for one random variable, that is e of xi, and this is for nth moment no moment of x. Both more or less both are same, but only thing is x to the power of n. Now the another important part here is the variance of random variable. Okay, of for a particular random variable x is denoted by v of x or var of x or sigma square. So we have already seen the mean value, then standard deviation, then variance of x in input modeling. So this is how we are going to find out this one. V of x equal to, so how I am going to find out this variance of x? Variance of x will be computed as v of x equal to e of x minus ex bracket complete to the power of whole square. So don't get confused. X minus e of x whole square, that's of that ex. Okay. Useful identity in computing v of x is given by this one, v of x equal to, so this is another important point that you need to remember. So v of x equal to e of x square minus e of whole e of x square minus e of x whole square. Okay, it is E of X square and it is whole square. Okay, this I will call it as equation 10. Now, the mean Ex is a measure of the central tendency of a random variable, and this is the variance of X measures the expected value of square root difference between random variable and its mean. So that's what he is talking here. Now, so with this, the variance V of X is a measure of spread variation of the possible values of X around the mean E of X. The standard deviation, and we have come across with one more value, which is something called as standard deviation, which is represented with small a. The standard deviation is defined to be a square root of variance sigma square. So the mean E of X, the standard deviation, that is rho, which is equal to square root of V of X, are expressed in same units. So this where we were talking about. So one example, such example which talks about the particular example. I have taken one example for this particular example. So you have to find out mean value, variance value, and the standard deviation. Now, if you look at E of X, what is the formula? The formula is sigma of xi into pi. So sigma of xi into pi, that is 1 into pi value is 1 by 21 plus 2 by 21. Like this, I calculated the values which I got it as 4.33. Now E of X square, same thing, only thing I have identified instead of X it is X square. So E of X square equal to 1 square into 1 by 21 plus 2 square is equal to into 2 by 21. Like this I have identified which is the value E of X square 21. Now what is the value of V of X? As I told in the previous slide, the V of X equal to E of uh, that is E of X square minus E of X whole square. So that is what I was talking about. V of X equal to 21 minus, so this value is equal to 2.22. So the standard deviation is equal to rho, which is the square root of V of X, which is square root of 2.22 is equal to 1.49. So that is, I think, that is what we have solved in the when the different types of data, that is in input modeling, we are talking about, we are finding out what are the parameter estimates. So where you have identified the x bar value, which is similar to E of X. Then later we have found the variance of X. Okay, then we have find out the standard deviation, which is the square root of V of X. So this is what the particular part. So